So this video is going to be about the scientific method and types of error that you're going to encounter when you're doing experiments. So the first thing we want to dive into is, what is the scientific method? Well, it's a set of concepts and ideas that are very good for solving problems. It's not a set order that necessarily needs to be filled out, but there are some general ideas that kind of make the most sense. We're really trying to generate why are we doing this is, well, we get an organized, logical method towards getting to a solution for a problem, or understanding a problem a little bit better, or situation a little bit better, why things do the way they do. Following the scientific method allows us to reduce redundancy in experiments. I mean, we don't want to copy what someone else has done, unless we maybe want to verify what they're doing, verify their results because we don't necessarily believe them, okay? But it allows you to do a new and original different things. We want to control for appropriate things in experiments, so we isolate variables. That's very important. We need to make sure that we have that independent, dependent variable are the focus of our experiment, and we can do our best to control all the other variables that might be manipulating the situation. Reduce the confounding of data with bias. So we want to follow the appropriate steps so we don't bring our own bias into something as much as we can. We want to make sure that we're sticking to what the data tell us. We can stick to the scientific method, stick to some of the basics there, and not try to take things too far, not bring our own viewpoint into it. Okay, we should be able to analyze our data and get the real results. We also be able to provide evidence for others so they can believe what we write, right? We want to be clear as to what conclusions we can draw and make sure they're applicable to the data that we actually acquire, not just kind of taking things and blowing them out of proportion. So, first, components of the scientific method. First one, we want to identify the problem to be solved. Pretty key, right? You make sure we have a single defined question we're looking at, and we know exactly what that question is. If we get too big, the experiment won't have enough focus. And if we don't really understand the problem, we can lead to some poorly designed experiments. So we want to make sure we know what that problem is and understand it completely. Second part, we want to gather information or background research. So that means reading about past experiments. It means going online, getting into journals, getting the papers, reading things that are going to give us the background information we need to make sure we have clarity of what the problem is, know what the experiments have done already, and see if we question anything about that experimental design and we can improve on that experimental design. Maybe technology's gotten better and we can fix some of the things that we think might have gone wrong or weren't fully explained with the problem in a previous situation. So that's why it's important to do background research. Then we're going to formulate a hypothesis. Okay, once we have our background research, we know what our problem is. We're going to make an educated guess about what we think is going to happen based on all that background information. Typically, it can be like an if-then statement, where if one variable is manipulated, it will change this output in some way. It can also just be a prediction of activity if variables can't be manipulated, right? So there may be situations you go into where you can't control the experiment. You can't control any variables. You're just going in and doing observation, but you have a picture of what you think you're going to see, and then you're going to observe to see if that fits the situation at all. Now, once we have our hypothesis, key here is we want to test it, right? We want to do our experiments. So we're going to design experiments to test the validity of the hypothesis. We want to make sure we keep an accurate record of all the data and the test conditions that we're using for each of those experiments, right? We want to make sure that we know exactly what the situation is when we run our experiments, so we know what the controls are and we can relay them to other people. And that way others can repeat and validate the kind of the results that we get. So what's necessary for a good experiment? Well, we want an independent variable. We want a dependent variable. The independent and want some control variables. We also want lots of different repetition, many different trials. So why are these plants here? Well, maybe the independent variable is the type of plants, is the type of soil that additive we're going to use in these plants, right? We want to give them a certain type of fertilizer to see which ones grow faster. Okay, so the dependent variable might be how high they grow, how big they get, how quickly that happens. Control variables, we would need to make sure we control the soil. We want to make sure we control the size of the box they're in, the species of plant, where the plant came from, how much water they're getting, how much sun they're getting. All those different things are control variables that we want to make sure we maintain. So that way we know that independent variable, that one we're manipulating, is the one that's causing the change in the dependent variable. We want lots of repetition. Okay, if you do an experiment once, somebody might not believe it, right? If you can repeat it in um, in lots of different manipulations of that variable. So for instance, if this was fertilizer, lots of different amounts of the fertilizer, okay? Um, and then we also want many different trials. So we don't just want to test one thing at one level, we want to test multiple things at that level. Those are all the ideals for an experiment. Sometimes you're able to do it, sometimes you're not. So now, observing and recording, next component of the scientific method, make sure you're writing down observations. Make sure you're writing about what happens during the experiments. Take measurements of the dependent variable during the experiment. Make sure you're actually analyzing what's happening. If you don't do that, if you just kind of wait to see what happens at the very end, if you're not taking notes along the way, you're going to be in trouble. So we want to make sure we're doing a good job note-taking, documenting what's happening in an experiment. The next part is drawing a conclusion. Well, at the end, was the hypothesis valid? Did we prove it to be true? Did we prove it to be false? And when you think about, was the experiment well designed? You might find holes in your data like, man, I wish I would have known this. I didn't think about this beforehand. I should have controlled this, but now I know that, so now I can make changes based on that. Next thing would be, did you have bias in your data gathering? Maybe you can look at that later and say, you know what, after I looked at this again, or had somebody else look at this, they told me, you know, you were looking for this thing when you started your experiment and you think you found it, but I don't believe you. So having other people to bounce that idea off of might help you think about whether or not your results are really true. Okay. Um, and in your conclusion, the big thing there too is really sticking to exactly what the data tell you. If you try to take it too far, okay, you're making what's called an inference. You're making a statement that you don't necessarily know is true. What you really know is true is what pertains to your experiment and your experiment only. So, kind of summary of the whole scientific method. One, there's got to be a question. Two, you got to do some background research. Three, there's usually a hypothesis. Okay, and you want to test that hypothesis, do your experiments, observe and record everything you're getting, and then draw a conclusion. Now, here's the thing. These are all major concepts. Does it need to be done in this order to do good scientific research? No. Lots of scientists have done great research where they didn't have a hypothesis when they started. They didn't even know what they were doing. They just went in and did some experiments to get some initial data, see what's happening, and then they went back and formulated a hypothesis based on that and tested it further. Some scientists can't do experiments. Okay? Some scientists are just purely observing and recording. Ecologists, zoologists who are going and studying animals out in the wild. Right? They may be just watching, viewing them, right? And seeing how they react to their environment. If you manipulate their environment at all, well, you're no longer having a clean experiment to see how they naturally behave in a situation. So not always are you going to be able to follow all these, and not always are going to make sense to follow all of these. But these are some basic outlines of good things that are appropriate for having a good, clean, logical way of solving a problem. Now, okay, we've got all this data, we've done our experiments, we've seen what we've got. Now the question becomes, how do we analyze it? Well, one thing we need to look for are types of error in the data. All the data you gather, even you do multiple trials, there's going to be some variability. And you're going to be maybe a little bit off from what you might have expected to get. Well, that's going to lead us to some error. We need to be able to categorize that error, classify it, understand where it might come from. So 2 types of error we're going to focus on, random and systematic error. So the first one, random error, it's about the variability of the individual data points, meaning how scattered are your data points? Are they clustered together in one spot? Are they spread all over the place? See here, these data points are all over the place, okay? But it does look like there might be a cluster if you look really close. Maybe in certain conditions, you do have clustered data here and here, okay? They tend to be less scattered around there. Maybe those aren't that random in those locations at those points. But for the most part, this looks like it would scatter. The smaller that random error, the closer the data points are going to be to each other. And the smaller the random error, the key is makes it easier to predict the results of any future trial. If you have 10 data points that are all really close to one another, it'll be really easy to predict where that 11th one is. So precision is kind of the measure of how close the data points are to each other. The level of precision determines how much the random error affects the outcome and the conclusion. You need multiple trials to know if your data is precise. So let's go through a quick diagram of that. Say I take one arrow dart and I throw it at the dartboard and it lands right there. I don't know if I have random error. I have one data point. I don't know where the next dart is going to land. But let's say I have a machine throw another dart and it lands over here. Now it looks like I have lots of random error. I have two data points. I have no idea where the next dart is going to be. There's a lot of scatter. I have very low precision and very high amount of random error. But if the third dart comes out here, and the fourth dart comes out here, and the fifth dart comes out right here, you can see that all of a sudden the effect of this outlier data point becomes reduced, and more than likely you're going to predict, well, that next data point is going to be right here. Okay. So by doing multiple trials, we can reduce the effect of random error on the average of all the data points and our ability to predict what that next data point should be and how good our conclusion is about our data. So we're always going to try to get as many trials as we can in an appropriate amount of time. Okay. Sometimes we're going to be limited, but we can reduce the effect of that one point that's way far away from our data or a little bit further off from our data, okay, by increasing the number of trials and increasing the precision of our data. Now, if the points are just all over the place, no matter what, we've got extremely high random error and there's no ability to predict, no matter how many times we shoot at this target. So that's important to understand. The other type of error is called systematic error. So here we have a small amount of, we have the systematic error because, well, it's all about how close the data is to an expected value. So you can see here we have a bunch of darts being shot at the board, but they're nowhere near that target right there in the middle. Okay. The smaller your systematic error, the closer the data is to the expected value. So in this case, we had a pretty high amount of systematic error because, well, we're nowhere near that target, that bullseye that we're expecting to hit. Okay. We have a bunch of data points. They're very clustered. So we have low random. Okay. We're very precise, but we have high systematic error because we're not near our target. So accuracy is all about how close the data is to an accepted value. How much systematic error do you have? So the key there, though, is there needs to be an accepted value in order to know if the data is accurate. Okay? And when you have these systematic errors, they're usually caused by errors in the system itself. Something's going wrong the same every single time, causing you to miss your target. So for instance, in this case, we take one shot and it's over here. In this case, we don't know if we have random error. It's one shot, right? But we already know that we have systematic error because we're nowhere near that bullseye. If that bullseye is what we were trying to hit. But if we were trying to hit, our target was actually up here, this little green box, okay? Well, then we have even more systematic error. So systematic error, again, is about how close you are to that target. We can have high precision, very clustered data, and very low accuracy because they're nowhere near that target. The one thing you can't have is very high accuracy with very low precision. So if all your data points are close to their target, it implies the fact that obviously they're all in the same place. So you can have high precision, low accuracy. You cannot have high accuracy, low precision. It's not possible. However, there's one thing that might throw you for a little bit of a loop. One time, maybe you have 4 data points that are spread out like this. This is where you need to be careful. If you take the average of these data points, well, the average of those 4 is that right there in the middle. So here we had lots of random error, lots of systematic error for the individual data points. When we averaged it out, it actually turned out that we looked like we were right on. So be careful if you end up in a situation like this. Make sure you're paying attention to those individual data points to decide whether or not you have systematic error or not. Last thing I want to talk about is what is a parallax. So parallax is simply an error brought on by a different viewpoint. Okay. For instance, in this drawing right here, we have person A, viewpoint A, we're looking at that star, and they look over here at these backgrounds, and they see viewpoint A, the person in the background sees the yellow star in the blue box. Viewpoint B, looking this direction, okay, sees that yellow star in the red box. So the viewpoint here changed the perception of the results. A thinks the yellow star is in the blue box. B thinks the yellow star is in the red box. Okay, and actually, in somebody looking straight on would say, "Oh, the yellow star is in the white box." Okay, that is a really ugly star, but whatever, I'll deal with that. So understanding that viewpoint can be a big thing. So when you are timing things and trying to figure out when something gets to the end point of something, make sure you're at that end point. If you're looking at from the beginning, you're not going to see it precisely. You're going to introduce parallax error. Now, understand parallax introduces a systematic error, or maybe a random error, but more than likely it's introducing a systematic error. It's not a type of error by itself. So having a bad viewpoint would mean that you're going to get the time wrong every single time by the same amount. Hopefully that makes sense. So, but these are some of the basic concepts of understanding like how we're going to approach problems and what are some of the errors that we're going to find when we actually go through and do some of our experiments.